Welcome everyone for topic 5. Now this is part 5. So topic 5 about knowledge, reasoning, inference and uncertainties. And in part 5 today we continue after this introduction about Bayesian theorem that we introduced in part 4. So in part 5 we explain it in more details in terms of some examples, so we can see that how this Bayesian theorem could be used for statistical inference and also in intelligent systems. Okay, let us go now to that slide. Okay, so last part we stop here about the basic form of Bayes theorem. So it is shown here in this form. So probability of event B, given that event A has occurred, equal to probability of event A to occur given that B has occurred times probability of B divided by probability of A, and we explained it through some simple example. Okay, so we can say here in this here that some briefly, an intelligent agent must update its belief when it observes a new evidence. A new piece of evidence is conjoined to the old evidence to form the complete set of evidence. Bayes' rule specifies how an agent should update its belief in a proposition based on a new piece of evidence. So this is the major thing, that when you have a new observation, how this new observation or the new piece of knowledge or new information, how this could be integrated with the previous knowledge or previous belief in certain proposition, if it is increased or decreased, or more precisely to say that how to have more precise uncertainty measure for some event based on the information, how to integrate this information in proper way. So this is the one at least of the features of using Bayesian theorem. Okay, so so let us go. This is the formula. So now we make it a little bit bigger to explain it more. So we have here the probability of B given A is called posterior probability that we are looking for. And this could be constructed based on the likelihood. This is called likelihood, the probability of A given B. And times the probability of B is priori probability, that probability that we know it before, about the general population, for example. And this called the model evidence, the probability of A. You can see that this model evidence, if you remember when we talked about this diabetic and person A, this is we said that B is being diabetic, and A we said that this is the age. Okay, so probability of the age is then how many in this population have that age. So it is nothing here mentioned about B. So it is not related to the event that we are interested in. So this is called model evidence. And actually sometimes when we like just to compare, because this is fixed, this one does not depend on B. Okay, so it is fixed number. And it is important, of course, to make the total probability equal to 1. Okay. So, however, sometimes if we just want to compare, not just for looking for certain probability value, but we compare which one is larger than the other. So sometimes we can ignore also this one and just use it as fixed number like alpha or something. We will see this in more details. Okay. So now let us start with example. So in this example, I will show how to use this Bayesian theorem in order to make intelligent agent that they want to fix a car. Okay, assume that in the morning that you found that your car didn't start up, and when you want to start up the car, you have start like to have maybe white smoke. So you have white smoke coming out from the engine, and the car did not start. Okay, so now you take the car to the garage in order for inspection. Assume now in the garage we have intelligent agent that they will try to fix your car. Okay. Now we define some parameters, for example. Okay, so we will say that the event A. Okay, let me use this one. So this event A is the car fault symptoms. For example, A, you can say that it is the car does not start. Does not start. And maybe also white, maybe smoke out from the engine. Maybe you can strange sound. Okay, and so on. So here A is the set of the symptoms of the fault symptoms that you observed in the car. So the symptoms that you saw them. The B is the possible reason. So based on this A, we might have many reasons. So we have, for example, B1. Let us assume that B1, I am not expert in car engines, so I will say something. So maybe maybe oil pump doesn't work. Problem maybe. Okay, B2, it can be, for example, battery. Of course the battery shouldn't make white smoke, but you can put all possible reasons. So because it can be also like a combination of them. So battery empty. Okay, and B3 can be anything. B4, so you have list actually of possible reasons for this problem. Okay, the intelligent agent now, they want to find what is the most probable reason for this fault. Okay, what we should do, the first thing that we have in this database of this garage, they have too many kind of faults they have like built over years of working, or maybe they buy this database from other garage or from other like provider, that they have all kind of possible faults that they have seen for this model, and also what was the reason. Because you know that when you have faulty car, you start to search, you start with some proposals that this might be this the reason, or that one, or that one, or that one. After a long time of searching, then you find the real reason. So finally you write in the report what was the reason and what was the faults and how did you fix it. So this is that all fixing like garage, they are working in this way. So now you have the database. Okay, so we have the database. Let us go to the white paper, so we can, to the note, so we can write like about this one. So we are looking about the probability of certain reason of the fault, given that we have the symptoms. So we have symptoms A, and we are looking for the probability of some reason Bi. This equal to, as we saw using Bayesian theorem, this equal to probability of Bi given, it should be the reverse, so yes, we can change the color maybe, or let us use, okay, equal to the probability of A given Bi times the probability of bi divided by probability of A. So this is now the likelihood. This one is the likelihood of the equation. Okay, now let me explain what everyone means. This one is the probability of certain reasons. So we have set of possible reasons, B1, B2, B3, maybe up to Bm, can be 100 reasons. Okay, the intelligent agent will make fast search in the database in order to calculate the probability of each of those. Okay, and now this is we have this database now. Okay, we have Septimus, we have Septimus A, okay, and we have the reason that we find B after of course many it cannot be only one septum, but it can be several septums actually. And then it can be not one reason, it can be also several reasons. Okay, B1, B2, B3. Okay, now the intelligent agent will calculate what is the probability of BI. The probability of BI, if we take the example that B is BI, or maybe a certain BK is the fault in the oil pump. Okay, as we mentioned. So we have oil pump, fault in the oil pump. Okay, now the probability of BI is what is the probability that the previous database we have this oil pump failure, regardless of the symptoms. So you can see here we don't have any symptoms, just the probability of, regardless of the sensor, what was the probability of that this oil pump of this car was damaged. So they might find that this probability was 0.03, for example. Then BA, what is the BA? The probability of A is what is the probability of having those symptoms regardless of the reason. Regardless of the reason. So maybe there are cars came, so those cars, they might have different symptoms or different observation. So this is the probability of A. So maybe the probability of A, maybe let's say 0.1, for example. Now, what is the probability of A given BI? This is actually the key here. The probability of A given BI, the probability of having these symptoms given that this fault happened. So now this will go to the database. Then we start to allocate where BI happened. So BI or BK, for example, for the oil pump failure. This is oil. I will make different color. This one is oil failure. This one and this one, and we might have another reason here. So, and now with this oil pump failure, we start to see how many out of those they have the same symptoms. So maybe for the symptoms we put them in the red color. So this one have the same symptoms that we have in this car, and only this one. So maybe we have only two. Okay, we have two the same symptoms, but we have 1, 2, 3, 4, and we have 4 the oil pump, but without with different symptoms. Then this could be computed from the database. Okay, they are 2/4, so it will be half, because the probability of having the same symptoms given that this oil pump failure happened is equal to 0.5. Then the probability of having that oil pump failure based on these symptoms equal to, in this example, it will be, for example, 0.5 times probability of BI is equal to we said that maybe 0.03 divided by probability of 0.1. Okay, so the result will be 0.15. Now this is the probability, or our uncertainty, or our confidence that this this symptoms was based on this possible reason, the failure in the oil pump. Okay, is that enough? No. because now the second stage is to find another reason. So there might be another reason, maybe the battery. Now they check with the battery and they found the probability, maybe it was 0.001. Then they check with other reason, third reason, fourth reason, fifth reason. Maybe, as I said there, that maybe we have hundreds of possible reasons. Okay, now the intelligent agent should select the highest probability. It means that the probability, I will put it here, maybe. So the probability of B I given A. So they calculate now for I equal to 1, 2, 3, up to M. Maybe M, as I said, maybe hundreds of reasons. Okay, now the intelligent agent should like propose or suggest BK, okay, which is equal to the maximum of BI for all I. So they check for all I, and they select BI for the maximum for probability. Actually, not okay. It is for the probability. I will BK equal to the reason that maximize for all I. Maximize what? Maximize the probability of BI given A. Yes. So they find the maximum probability that it causes these symptoms, and then they start with it. Okay. So working or not. So they start checking this reason. If this was not the reason, then they might go to the second possible reason. So this is very simply, very basically how this Bayesian theorem could work with this intelligent agent in order to find the fault in certain car or fault allocation. Okay, actually the same thing that could be done in hospital for patient with certain symptoms. Then what is the possible reason that they can be those symptoms? Based on that, the intelligent agent doctor might request some analysis, some blood analysis, in order to enhance its belief or the reverse, so they can change the possible reason. So this is actually the way how it works. Yeah, this is the explanation. I hope that you will read these. Okay, so this is the conditional probability. So we know that the same formula, it can be put in this way. So the probability of BI given A for any in general form. So it is actually the Bayesian theorem, but here BA actually, the probability of A could be also represented somehow as the multiplication of the as far as BIs are like disjoint events, then it can be represented in this way. Here we have some interesting examples. So it is very simple example explained in this slide. So please try to study it. Okay, and now I like to go to this football robot team. Assume that we have intelligent players. They want to play a football, and here we assume that each team they have only 3 players. Okay, so assume a football robot game. There is an intelligent agent in each robot that decide what to do. Assume there is no communication between robots, so if each robot should decide by itself. Hence, each agent should decide for itself what to do. Assume each team has 3 players, and the goal is to pass the ball inside the goal of the opponent team. It is just football game. Each robot has 3 options to do. Okay, either shoot the ball toward the goal of the opponent team, pass the ball to the second player, pass the ball to the third player. So we have this is the game. So the game here, that the ball now is there is sensors for each robot. So the ball is now close to this robot. So this robot will think what to do, or what is the optimum way to do. Is it passing the ball to the second player? So they are the blue blue like game or blue team, or pass the ball to the third player, or shoot the ball toward the goal of team 2. So they have only 3 options, and we like now to see how to select the best option, how to select for this intelligent agent, how to select the best option based on the statistical inference. Okay, so to do this in simple way, so we assume that or we define 3 events, or 4 events actually. A, pass the ball to player 2, assuming that the player who has the ball is player 1. Pass the ball to player 3. C, shoot the ball directly toward the red goal. H, score goal. So this is actually the score goal that what we want to have. Okay, now the agent in the player 1 should be able to compute or estimate the following probability. What is the probability of scoring goal based on passing the ball to player 2? What is the probability of passing of scoring goal? Of course, here scoring goal maybe not directly, but the game which ended by scoring a goal. Okay, after we can of course define like some number of steps, like for example 3 steps. If it doesn't happen in 3 steps, then we don't consider that it is a scoring goal. Okay, so this is the probability of a scoring goal if it is passed to the ball to player 2. Probability of scoring goal if it is passed to player 3. Probability of passing scoring goal if it is passed to or it is shot directly to the goal. Okay, now we have 3 probabilities. So simply that the player or the agent, once computed these 3 probabilities, they will select the maximum one. Okay, but now how to compute them? Computing them, if we take, for example, this one, probability of H given C, probability of H given C is equal to probability of C given H times probability of H divided by probability of C. Okay, what is this one? This one means the probability of scoring, scoring goal, given that the ball shot directly to the goal, is equal to the probability of the shooting the ball, given that goal has happened. It means that this player will, from this location, will compute from its previous experience what was the probability of that times that when they shot the goal, they have that scored goal. Okay, so given scored goals, what was the probability that happened because they shot it directly? So this can be like computed from the history times probability of like scoring goals in general, and this is the probability of shooting to the goal in general, without or without any calculation if a goal like scored or not. So this is the formula here. How to build this formula? We need database again. Okay, from where this database came, actually you can see that if we bought such like toys to play together and we start to update their own like probabilities during their playing, so we can see that how this will be improved with time, because it is like increasing the experience. They can improve the accuracy, how to select the right action based on its location. Of course, now I put it in very, very simple way. However, to be more accurate, we can also add other things. For example, the field. If we like just divide the field into squares in this way, okay, then of course we have here the goal of maybe one team, and this is the goal of the other team. Then where is the location? Where is the location for the player? Assume that now this is, we have the player is here and the ball is here, okay, and we have another player that when the same team is here and the player is here. Okay, now by adding the information of the location, it becomes now what is the probability of a scoring goal given that they shoot the ball directly, okay, and given that the location of the player. Now the location, we have the location. With this information of the location, okay, maybe this agent is too far from the goal. Okay, and according to the power of the shoot, this will never score any, for example, if L greater than some alpha 0, this will never that score the goal because the ball will not be enough to reach to the goal. But how to recognize that? Recognizing that by experience. So in the beginning, each agent will start randomly, that they do just shoot or pass. So we just inform them what operators they can do. As if we go back to topic 4, when we talked about the intelligent agent and the operators available for each agent. So now we inform the agent only what actions that they have. You have either to pass to player 2, pass to the player 3, or you can shoot directly to the direction to the goal. This is what they have. Okay, now within these operations, they have information. In the beginning, they will start randomly. So they start with anything. So they start to shoot. And then they see that if it is goal or not, it is not goal, shoot again, not goal, shoot again, not goal. So maybe after many times of shooting from this location, there is no goal, then the probability of shooting will decrease at that location. At that location, even we didn't inform the intelligent agent that with that location you will not be able to score, but they will deduce this information or this inference by itself, based on these equations. So I hope that this clarify what we mean by the statistical inference. We don't have to put many things, or preload many things to the intelligent agent. They can build their own experience, their own knowledge based on this statistical formula, which actually not difficult. Actually, it is quite easy to compute and also to update. So the statistical inference is very important, and this Bayesian theorem, how to use them, actually they are amazing. Okay. There are more explanation about this problem. Okay, so you can, I made it here how to make some computations as well and so on. Yeah. Of course, you can increase. This is what I mentioned now about increasing or using the location. You can make it like more dynamic game. More dynamic game means that you include also the time. If you include the time and the movement, so it means that you have a camera, but if at each time you will decide what is the best location to move, because as I mentioned now that we have this field, we divide the field into squares. Of course, as more squares you have, as more accuracy that you will have about the movement, but more complicated terms in terms of computation. Not because when you have too many, then you need to have too many also searching techniques. Now we have the searching techniques. So if the player is here, if our agent is here, so now we have not only 3 options: shoot or pass. This is the second player. The third player is here, for example. This is the third player, second player, and this is our player, and this is the ball is here. So in previously that we have either shoot or pass or pass. Now we can have another strategy or another rule that you can move. So you can move to forward with the ball, backward, to the right, or up and down, and maybe also crossing in this one. So now we have 1, 2, 3, 4, 5, 6, 7, 8. So they can, for example, walk into 8 directions by 1 step with the ball. So when they move if the probability of scoring from the new square or from new location will be improved or will be increased. Or not only the shooting, but maybe the passing, the success of the pass of the ball to the second player will increase. How to build? You can see it looks very complicated, but actually mathematically it is not. Mathematically, that it is based on all of them, based on the Bayesian theorem. In the I start this is important to remember that in the beginning, if we don't have any previous database, so that those intelligent agent may start to like do just random things, just pass, shoot, move, and so on. So they start to have it in a random way, but with time, they start actually not random without computation. They make random actions, but at the same time, there is counter inside, like their simple microcontroller. So there is a counter, and there is simple computation algorithms. They calculate all the time, and after like thousands of movements, you can have that expert player. You will have expert intelligent agent that they can play in nice way. Sometimes it can be also surprising you that how they could move and how the decision they will make based on this simple Bayesian theorem. Okay, and in that case also maybe this knowledge could be after that like uploaded to a new player, so they don't need to start from scratch. Okay, what else here? So here we have the same that we explain more about this intelligent team. Okay, now Bayesian inference intelligent agent classifier. Actually, it is very similar to what I have now explained, but now we can take another example. Assume here that we have n possible classes, okay, for a certain system. For example, in different diseases, in possible fault location, in business situations, and so on. Assume also that there are m available associated attributes or features. So this is the things that we are or the observation that we have. Okay, and we like to classify based on these attributes in which class that we have. Okay. Our actually Bayesian inference, like based system or intelligent system, it is able to automatically classify in new cases into most probable class. Let us have example. Assume, for example, that we have intelligent robot medical doctor that looks to a patient with certain symptoms, but also they have certain attribute: the age, weight of this person, the body mass index, temperature, blood pressure, smoking or not, blood test, and so on. So we have certain attributes of this patient, and we have symptoms. Then the doctor should be able to classify this patient or these symptoms on which disease that most probable that to have. It is the same as I explained now about also the fault in the car and how to find it. Okay, so now what we have the probability. What is the probability of certain class, given that we have, as you can see, certain attributes. We have symptoms, we have attributes from x1 up to xm. In what is the probability of being in class 1 or class 2 or class 3 up to class n? As I said, this could be applied in different areas. It can be in medical side, in fault location, in manufacturing, in social system. So it can be in any application. Okay. So the idea here that we can build directly using the Bayesian theorem. Okay, with the Bayesian theorem, the probability of Ci given the attributes equal to the probability of attributes given the class times probability of being in the class divided by the evidence or the probability of those attributes. Okay. Now, which one that you will select? Which one? Of course, once this one can be computed from the database, as I mentioned before, and then we select the class which has the highest probability assuming, and this is actually very important to remember, assuming that all decisions have the same risk or for wrong classification. I give you example, simple example. So if we have like intelligent doctor or intelligent agent doctor, like automatic doctor classifications that classify the diseases, and they receive like old person, maybe 65 years old, 70 years old, and they have some chest pain. Okay, and once they have the chest pain, the other attributes of this patient that had heavy dinner in the night. So in the morning he started up with chest pain. So of course there can be many reasons for this chest pain. One of the reasons that because of gases in the stomach, it can muscle attraction, just normal muscle attraction that you can take just some painkiller and that's all, and it can be also heart attack. Okay. Based on the history in the doctor or in that intelligent agent system, based on the history, we find, let's say, 80% of cases was due to some like muscle attraction. So it is not at all serious case, and only taking some painkiller that's enough. And also the second probability that or this is the 80%, maybe we have 15% that because of gases in the stomach, there's 3% because of this and that, and there is only very small probability that to be heart attack. So the probability of being heart attack is only 1%. Do you think how the intelligent agent should work? Because if we deal just with numbers, of course they will say no problem, and they will take the highest probability, but this eventually will be wrong, because it is not possible to say about, because the risk is not the same. The risk is not the same. If even the probability of being with heart attack is only 1%, but they must start with that one. So selecting the highest class probability only, remember, only if the risks are the same, if we have the same risk. Otherwise, we need to modify this little bit to take into the risk into account in our decision. And this is, of course, in automatic decision making. Okay, so many times actually it is hard to compute the probability of having all these attributes together. For example, attribute 1, 2, 3, 4, and all these attributes, to have them together, you might need very huge database. For example, someone, he has such kind of body mass index, age, and that pressure, and maybe height, and maybe too many attributes, and to find them together in another person, the probability is very, very small. So otherwise you need very large database. So how to handle this problem? We of course, those parameters, they are dependent. Remember that we cannot say that the BMI, for example, and weight is not dependent. They are dependent. Okay, and we cannot say, for example, the pressure and the weight of people, blood pressure and the weight of person, they are not independent. They are somehow, they are correlated at least. Okay, so how can we solve this problem that we cannot have all them together, or it can be very hard to have them together about this evidence, or also about this one? Because they are dependent. However, we can assume they are independent, and once you assume they are independent, so you can multiply the probabilities in each other. This is called naive Bayesian classifier. So by assuming this, they are independent, even they are dependent. However, it has proved that this works fine as well. So to improve or in case that you don't have very huge data, so you can assume the independency, and you can still work with the naive Bayesian classifier and get good result. The final thing here that we have a numerical example about this using the classifier based on Bayesian theorem. And here we assume that we have two classes A and B, and we have two attributes x1 and x2, and then we show here in this simple numerical example how to find. So please read them from the slides and study them, so it gives you just a general idea how this work. Okay. The rest of the slides actually just we talk about random variables and talking about some general things in the probability. So what is random variable? Actually, it is not a variable, it is a mapping that instead of talking all the time about events that tail or head, or we have draw a ball, or we have 5 balls and 3 and this person has like diabetic or not diabetic. So those are events, so they are descriptive events. Okay, so it is better in probability theory that we deal with numbers. So the random variable means that we give a number, we give real number for this event. So for example, head, we bought, for example, for head we say that head means 1 and tail means, for example, 0. Okay, so in this case we can easily say what is the probability that x is the outcome, that x equal to 1. It means that what is the probability that you have head. But now we deal with numbers. When we deal with numbers, it becomes easier even to draw. For example, here 1 means head and 0 means tail. But we don't put, if you come to the number line, and you cannot put head and tail, but you can put 1 and 0 here. Okay, and then the probability of 1, it can be, for example, 0.3 in this example, and here we have 0.7. The total is 1. Here 0 means tail and 1 means head. You can also say that what is the probability that cosine, for example, x by equal to, for example, 0. Okay, so now you can calculate what is the probability of x by equal to or by over 2 equal to 0, because now you deal with numbers actually, and x can be 1 or 0. So the probability of 0, if x equal to 0, cosine 0 equal to 1, and if x equal to 1, cosine by over 2 equal to 0. So it is actually the same. This equation is the same as that you have probability of head. But what if we said that what is the probability cosine x by over 2 that equal to half? Okay, so now we don't have x that equal to half, then this probability equal to 0, and so on. So dealing with numbers makes things much easier. We can build easily algorithms to deal with these random events. So this is the meaning of random variables. Okay, it is not variable, it is a mapping between the events space to numbers space. Okay. Yes, here is just explanation about these concepts, and after that we gave a few numbers of distributions, like binomial distribution here, and some examples. We have geometric distribution. We can have also continuous random variables that not only discrete as head and tail. We can have continuous, like temperature, for example, and so on. Actually, and here we have some distributions. Because of this course is not that very long course, so we just give them for a general, very basic one. But we have another course is machine learning course, where it is based on these algorithms, where we explain those in much more details. We have the famous normal distribution or Gaussian distribution here. We explain it a little bit, and then we have COVID-19 diagnostic exercise. Yes, so that's all about this topic 5, and now I hope that it is clear when we talk about reasoning in logical way, and when we talk about statistical inference and Bayesian theorem, conditional probability, how things are looking together, and how to build, for example, some simple examples or simple classifier based on the statistical inference. Thank you very much, and after that we start topic 6. Yes, thank you. Bye.